Hello everyone and welcome to our talk on a novel approach for finding missed optimizations in compilers. Compilers are incredibly good at optimizing programs. However, they are also very complex engineering projects that keep evolving. New optimizations and analyses are being frequently added, and existing ones are frequently updated. But even a simple case, such as this program, can be a challenge for modern optimizing compilers. This program contains a zero initialized integer that is also static, meaning that the compiler can be sure that no external piece of code can modify its initial value. Therefore, when main executes, its value will actually be 0, and then checks if that value is non-zero, in which case it returns 1, else it returns 0. Obviously, this program can only ever return 0. And thus, it's not unreasonable to expect that a modern compiler will optimize it down to these two instructions, essentially just returning 0. However, if we use LLVM or GCC at the highest optimization level, we can observe that both of them generate code for essentially every part of the program, both for the, as highlighted, both for the if check, the return one, and this dead store 2a. Both of them are missing an optimization opportunity. And the goal of this work is to automatically find such missed opportunities in compilers. And to do this, we needed to solve three challenges. First of all, we needed an optimization oracle, a way to gauge whether optimizations have been successfully applied. Now, the problem is that there are a plethora of different optimizations in compilers, and therefore we need something generic that can capture a large variety of them. To that end, we use dead code elimination, which in itself is such an optimization. The second challenge is being able to detect that an optimization has actually been missed. For that, we use differential testing, a standard technique that compares multiple implementations of the same approach or system and compares their outputs. In our case, we use multiple compilers and compare their optimization capabilities. The third challenge was that even if we actually detect that an optimization has been missed, we must also be able to localize it in the exact part of the source code that is affected, such that we can reduce the test case and have something that is actionable and understandable. For that, we introduced the concept of optimization markers. Using this approach, we reported more than 80 such performance bugs, most of which have been confirmed and a quarter of which have already been fixed. So what does make DC a good optimization oracle? The first important property is that it is an optimization sink. For example, in this program, to determine whether this piece of code here, the if statement, is dead, first the compiler must rely on alias analysis to check whether the two pointers point to the same addresses. And similarly, DC has to rely on many other transformations, such as I already mentioned, alias analysis, constant propagation, and others. And if DC is successful, it implies that these were also successful. And on the other hand, if DC is unsuccessful, it may indicate that one or more of these analyses or transformations were unsuccessful. The other important property is that dead code elimination should always be applied, because there are a variety of gains by doing this. First of all, it reduces binary size. There is no reason to include code that can never be executed in the final binary. It also prevents redundant work. The compiler doesn't have to analyze or try to optimize code that can never be executed. And more importantly, it simplifies code, and therefore it makes it easier for the compiler to perform further analysis and optimizations. And all of these mean that the compiler doesn't need to use some sort of heuristic to decide whether to apply dead code elimination, but it always tries to apply it. But now, given that we have this oracle, how do we actually detect that it is applied or not? I will demonstrate this through an example. Here we have a piece of code with two highlighted if statements that are both dead. Their conditions are always false. If we now use GCC to compile this code, we can manually inspect that it actually failed to optimize away both of these checks. So it generates code for both of them. But manual inspection is obviously not the solution. It doesn't, first of all, it doesn't scale to large programs, but also it cannot be part of a fully automated approach. But what we can do is use a second compiler, in this case LLVM, and then we see here that LLVM eliminated the first if statement, meaning that it's actually dead. Therefore, we can deduce that GCC has a missed optimization opportunity. But this does not solve the problem of being able to automatically find these differences. And for that, we introduce our next insight, which is optimization markers. The purpose of an optimization marker is to include an indicator in the generated assembly that makes it very easy to detect that a certain dead part of the source code has not been eliminated. And we implemented these markers as function calls, but there are other possible implementations, such as compiler built-ins. What we do is to instrument all constraints that affect a program's control flow. In this case, we have if statements, but we also instrument for loops, switch statements, and so on. So now if we compile the instrumented program with GCC, we can directly search for the markers in the generated assembly, and we can see that GCC has not eliminated any of the two. And if we use LLVM, we can check that LLVM has eliminated marker 1, but has not eliminated marker 2. So what we can infer now is that very easily and fully automatically is that GCC is actually missing marker 1, and therefore it's not eliminating the corresponding if statement. And the important property is if markers are eliminated, then the surrounding block that contains them has also been eliminated. In this case, we used two compilers to perform differential testing, GCC and LLVM, but we can also do this with a single compiler. For example, by using two different optimization levels. If we run GCC, say, at 01 and at 03, and it manages to eliminate a marker at 01 but not at 03, then this means that we have a missed optimization opportunity at 03. Something is amiss. What we can also do is use the same compiler at the same optimization level, but at different versions. So we could, for example, compare the current version with the previous one, or the current version with a development branch, such that we can track regressions that were recently introduced. What we can also do is be very precise by controlling a single commit, and we can do this by using one version of that commit and one compiler version that is the previous commit. And then we can pinpoint or we can scrutinize single commits before they are integrated in the compiler. What we can also do in this case, because it's a deterministic and closed program, meaning that it doesn't take any arguments, is that we can execute it and measure which markers are actually dead. So we can compute the ground truth. And we use this for our analysis that we did in our paper. And in this analysis, what we try to answer is how good are compilers at DC, and as an extension, how good are they at optimizing code? And to do that, we needed a test corpus. And for that, we used 10,000 test programs that were generated by CSmith. CSmith is a randomized C program generator. And now, because these CSmith programs are closed and deterministic, we can also compute the ground truth. And what we computed was that these programs contain around 3 million dead blocks. And we used GCC and LLVM and various optimization levels and checked how many of these dead blocks they eliminate. And unsurprisingly, at higher optimization levels, the compilers were able to generate a larger subset of these markers, but they were still not able to eliminate all of them, meaning that there is still potential for improvement. The second question we wanted to answer is whether differential testing based on DCC is actually feasible. And we evaluated two scenarios. First, across compilers. And here we checked whether there are dead blocks that GCC is missing and LLVM is not, and vice versa. And in both cases, we see that there are a couple thousand of these. We also evaluated what happens if we use a single compiler and compare across optimization levels. And we also find several dead blocks that are eliminated at 01 or 02, but not eliminated at 03 at the higher optimization level, showing that there is potential for finding missed optimization even on a single compiler version. We also analyzed a subset of the missed optimizations that we found in order to determine which compiler components were affected by them. We found that indeed DC is an optimization signal that is relying on a large variety of the compiler's internals. For example, loop transformations, the pass management, peephole optimizations, and so on. and this confirms our hypothesis. As I mentioned in the beginning, we used our approach to find more than 80 such performance bugs at the time of submission, and we reported them. And a lot of them have already been fixed, but in the meantime, we have kept finding and reporting more, and the response of the compiler developers is very positive. One interesting thing that happened more than once was that we reported a regression that was fixed by a developer. And then later on, we discovered that a new regression was introduced by the very fix that fixed the original one. And we reported it again. And this really surprised the developer, which had to also fix that. And this really highlights the need for such automated ways of checking new code that is introduced to the compilers, such that the chance that new regressions and new missed optimizations are minimized. And as an example, here I show one such missed opportunity that we reported. The important part of this piece of code is that there is a check here that checks whether this array, C at position 0, contains a non-zero address. And the important thing is that this can never be true, because C is initialized with the address of this array entry. And therefore, this piece here is dead. And indeed, if we use GCC at 01, it can detect that and can eliminate this piece of code. But GCC at 03 could not. And the reason for this is that the loop at 03 is being vectorized. However, GCC vectorized pointer data, in this case C star, as unsigned integers, but they are signed integers. And this prevented propagating the knowledge that the address of A1 is actually assigned to C down here, and then the compiler could not actually eliminate the piece of code. We reported this and it got fixed for GCC 12. Here is an alias analysis related missed optimization opportunity. Similarly to before, GCC could eliminate the marker at 01, but it could not at 03. And the problem was that it could not figure out that the pointer D does not cannot point to the variable b, even though they have completely separate types. Another example of missed opportunity is shown here. This piece of code contains a lot of complicated arithmetic, but the important part is that that variable e, after all this arithmetic, is equal to 0. And indeed, version 13 of LLVM at 03 could eliminate it, but the development version at some point lost the ability to do so. And here we demonstrate also that our approach can find regressions using a single compiler at different versions, either different major releases, or we can compare major release against the development version. And what happened was that there was a regression on peephole optimizations on shifts. So a change that was supposed to introduce more optimizations on shift operators actually introduced this. We reported this, and it also got fixed. In this example, also involving arithmetic, LLVM at 01 could eliminate the DCE marker, but not LLVM at 03. And the problem was that after some simplification, the compiler could deduce that operands of this module operator were constant ranges of a single element, but it could not simplify these. Even though for other binary operators, such as the logical AND, it couldn't do it. And this was an omission by the compiler developers. We have implemented our approach in our tool that is available at the displayed link. There it can fully automatically generate such reduced test cases, and our hope is that compiler developers will include this in their standard testing facilities, such as they check every commit and release for potential missed optimizations and regressions. In conclusion, we presented a new approach on automatically finding missed optimization opportunities in compilers, and we relied on dead code elimination, differential testing, and optimization markers. In total, we reported around 80 bugs, a quarter of which have already been fixed. We also used our technique to analyze the ability of compilers to optimize code, and we also show that our technique can find missed optimizations and performance bugs in a variety of compilers' components. And finally, we have implemented this approach in DED, which is available on GitHub.